Our next planned presenter, Dr. Cenk Kocer from the University of Sydney, could unfortunately not travel to the conference this year due to some medical issues. But we have this former colleague here, Dr. Antti Aronen. Antti, where are you?
Yes, thank you.
Ah, very good. Antti is co-author of the paper and worked about 10 years ago for 4 years at Dr. Kocer's research group at the University of Sydney. And one of his main topics was thermal and mechanical modeling of vacuum insulating glass. Currently, Antti is working at Glaston in the process development of heat treatment processes. And the title of the presentation is The Thermal and Mechanical Performance of Pillars in Vacuum Insulated Glass. Please welcome with me Antti Aronen.
Thank you. Thank you. Hopefully everyone has time to sit down and then we can start. A couple of words at first. So I hope that after this presentation you have understand why there are pillars in a vacuum insulated glazing, what are their performance, and how they are affecting in a VIC in thermal and mechanical way. If we start from what happened 30, 40 years ago, at the University of Sydney, they started a research about vacuum insulated glazing. Here are some of the first samples, what was done at the late of 80s, beginning of 90s, and then at the end, there was first products of VIC made, and that was the product what was in use for NSC as spatial glass. So there are typical things for VIC, 2 glasses. At the edge there is solder glass, which make hermetic seal between 2 glasses, and then there needs to be pillars to keep that gap between 2 glasses, so that there is when vacuum is coming there, those glasses don't touch each other. And then there was at that time pump out tube which was used to make this vacuum between 2 glasses. In the early days, 100 years ago, when there was the first research or first publications about VICs, there was a lot of talking about pillars to keep that vacuum gap in a VIC. But lately, there has been lots of work going on with pillars. There are different kind of pillars. Typically, pillars are metal pillars or glass pillars or some other material which can handle that force what is coming due to atmospheric pressure, and at the same time won't break, can be a little bit lubricated so that they can slide on glass surface. There has been other versions, ceramic pillars, what has been printed on glass surface, and then in heat treatment processes made those hard ceramic pillars with a different kind of features on glass surface. Even with laser, you can form pillar at the top of a glass surface, so that the dark part is that pillar what is made on that. But what is the thermal effect on this VIC on these pillars? So pillar is kind of bridge between two glasses. So there is heat is flowing from one pane to another pane, and there is conduction through that pillar, but there is also spreading what is coming when heat is flowing from the larger area to a pillar and then spreading again. So there are two things which are both combined to make resistance between the two classes. And if we look what's the role of that material, what is used for that conduction. So here is on the x-axis there is thermal conductivity of that spacer material, and on the y-axis is thermal conductance of a whole pillar array. So you can see that if we are staying at thermal conductivity over 1 for that pillar material, that effect on whole thermal conductance doesn't change much. So it's more about this spreading resistance, what is coming on the glass. But if we go below 1, then you start to get advance from that material. So it needs to be some kind of a glass material, ceramic or something like that, if you want to really go to better resistance for the pillar case. But then there is a problem that do you get material or find material which can handle that force, what is coming on glass from the atmospheric pressure to that pillar. And if we think about parameters like size of a pillar, what's typically diameter of pillar or spacing between pillars, those both have an effect on how this the thermal conductance is behaving. So on x-axis there is a spacer radius. If you increase the size of pillar, that changes total conductance of the VRC. And also if you are increasing spacing, then that way you can also lower the U value of the VRC. But there is a kind of linear behavior for spacer diameter radius, but in the power -2 when you are increasing the spacing between pillars. So kind of you should use as small pillar as possible and put those as far away from each other to get best thermal performance. But problem is that when you think about the mechanical things, there are coming some stresses on the glasses. So here are some points where you can see which can be problems in a VRC, thinking about the strength and forces. So first thing is pillar. You get that compression due to atmospheric pressure, so it will be squeezed out and the thickness will change a bit. So that needs to be strong enough material to handle that force. Then due to a contact between pillar and glass, there is a Hertzian indentation, and that will cause the probability for cracking of the glass on that glass pillar contact. And if we go outside of the glass gap, then there are forces which are coming due to deformations of the glass. So between the pillars, glass is bending, and then on top of the pillar, you get the higher stresses which can cause cracking of the glass. Or at the edge area, when the edge doesn't push down when you apply that pressure, but the pillars are getting a little bit shorter, that is causing stresses around the edge areas, like here. So those things need to be taken in consider, thinking about what kind of pillars you are using, what kind of spacing you can use for those ones, and so on. Here are some examples from previous later days where you can see that what can be problem. So at first, here, not sure how well it's able to see, but there is pillar in the middle. There are two other pillars, and between those pillars, thin glass is bending. And because that gap between two glasses or thickness of pillar is usually around 0.2 millimeters. If that glass is bending a lot, you can get the touch between pillars, between glasses, and that can be seen as this kind of Newton rings. And that can be a problem. It's causing shear stress and shear cracking between those glasses, so that can break the glass and cause that vacuum is getting off from the VRC. On the right-hand side, there has been happened the cracking on the glass outer surface because glass has been bent over the pillar, and it can also cause that if that crack is getting deep enough, it will break the glass and let air in and the vacuum out. So those things need to be avoided, and for that one, it needs to be designed what kind of material and spacing and size need to be used. So here is an example that here on the left side, on the x-axis there is glass pane thickness, on y-axis spacer distance, and you can see that if this distance between pillars has been changed from 20 millimeter to 40 millimeter, glass is bending more. It's increasing from 2 micrometer to 12 micrometer. Okay, for that, for visual things, it's not big, but it can cause problems and need to be taken in account. So if you are using even thinner glass, that can make it visible, and that may be problematic. But bigger influence is when you're increasing a distance between pillars. Can be seen from this side, where there is how stresses above that pillar on glass outer surface increases. So if we think about the long-term stresses in a glass, according to the standards, that the normal float glass can handle 8 megapascal stresses only for long term. So that's why you have to go low enough stresses on the outer surface where there is a humidity going on or involved in that glass, so that you can really be sure that it will last 20 years, 50 years, even those PLCs. But if you increase that distance between the pillars, you start to get higher and higher stresses above that pillar. And then you need to think about, okay, how I can handle that stresses. And for that one, you can use heat strength glass or tempered glass even, so that you can be sure that those stresses doesn't break the glass, so the glass can handle, or even chemical strength glass, or some other way to be sure that it won't break that easily. They are also on the contact side, so between those glasses, there are risk of breakage, but there is no water. It's dry atmosphere with vacuum, so you can have higher stresses inside without the breakages. So behavior due to humid air is so big that this can help. So in case of, for example, when you get the impact to a VIC, those pillars get to go smaller, but at the same time you get shear. So there is a different kind of combination of stresses. If we at first look when there is a normal force due to atmospheric pressure, there is difference if that the pillar can slide on glass surface or if it can't. This results with squares, that's with the full slip so that it can slide even, and results with the circles, those are for the case where glass pillar cannot slide really to glass surface. From these ones, the important thing is that where you get tensile stresses. And that's in the case when you have a full slip. So that's bad case, because that causing stresses which can cause glass breakage and coming of this kind of conical cracks. So that's what you should avoid. But in a case that you have a full slip, you don't get that much shear stresses, which is another point. But at first, when here is results about this normal force. So if our pillar radius is increasing, then we can go higher and higher so that conical cracks doesn't happen. For example, when half a typical diameter for pillars is half a millimeter, then you can go up to 50 millimeter separation between pillars. If you go smaller, then the limit for that you start to get cracking due to normal force on a glass surface. That's decreasing. But there is combination between these ones. Thinking of how that glass behaves under only that pressurized load. But for shear stress, if a pillar is on glass surface, it tries to move. It will make deformations on the glass surface, and it will cause stresses. So before on the outer surface, we are talking about 5 to 10 megapascal or higher stresses if there is a tempered glass. But for the internal surface, for the shear stresses, we are easily talking about hundreds of megapascals. So if we have a pillar with lubrication on glass surface, that way we can increase or we can lower those stresses what are coming on a glass surface from a shear, and that way avoid those breakages due to impacts or bending or other things. So if there are cracking of the glass, not sure how well it looks, but in this case, glass has been dropped with the bore drop test, and even though it looks like impact has been on the left of the corner, and there is a lot of cracking, the initial fracture point has been in this area because of there has been a high shear stress which has caused that initial fracture. So even though at the top left corner there has been this conical crack, it doesn't have been go through the glass, it's just on the surface. It will look bad if you look visually, if there's only that one, but when the glass breaks, it can be that it's somewhere else due to other reasons. Same thing in this one, bore drop test. Photos from bottom side, there are four pillars. And when glass has been bent, there is shear stress, normal force, and initial cracking has been happened in that corner. And then you can see that even though highest stresses in glass are in the middle, that's not the initial fracture point, but all the cracks are growing that way. So if we combine these two things to design what kind of pillar array, pillar size we can use, we can plot different kind of curves. So here are U values with the different emissivities. So we want to get as low U value for the glass as possible. But there are some restrictions. For example, this purple line is coming from when the pillar gets a compression, how much force that the pillar can handle. Light blue one is visual distortion, how bad does the glass looks like. And then red one is pillar indentation, how much that happens. So all those three cases, you have to stay here on left side so that it can meet the strength and bending of the VRC. And then there is this green one, which is coming for the stresses above that pillar on the outer side. And from those ones, you can match where is the good combination so that glass can handle those stresses, but at the same time you get the good U value. And if the stresses are getting too high at the outer surface on that green line, then you can increase the tempering level of the glass and meet those requirements. And this case is for 3 mm glass and 0.25 mm radius pillar. If you change thickness, size, those curves are changing. And you can, again, use the results to design a good combination for VICs. And because there's thermal bridge, you can sometimes see from a VIC that instead, when one outer surface is getting cold, it gets a frosting due to condensation, but you can see clear spots on the pillar placing, and that way, that's one thing why thermal bridging over pillars is not good thing, but it can't be avoided. Thank you.